Hello, this is Graham. It's August the 4th, Sunday. I'd like to talk about the SI units for these two diagrams. So we ignore the jerk functions and we just look at current, charge, voltage, and the magnetic flux density, Tesla, and velocity, the gravitational pull, length, and what I call the Higgs field include, or it's mass, or magnetic mass as it's known. What I've done is I've converted all of these to their SI unit equivalents, which you can see here. So current is in amps in the gold, seconds is in gold. I know I said this was the S-plane Laplace, but in this particular two diagrams, everything in gold is actually what it says on the tin. That is indeed seconds. TV means velocity-based time and acceleration-based time. That's an important one because when you have u equals a half at squared, the t squared simply means ta times tv. Okay. What we have is charge is equal to amps times seconds, and volts is kilograms per amp multiplied by meters squared seconds cubed. Velocity is meters per second. And what we do here is we say, okay, look, amps is something you measure on a meter, but it also has a drift current, a drift velocity. So we can describe it as something that's in meters per second, and that's totally valid, because in here, when we substitute A with meters per second, what we get is we divide by M to drop this one down by 1, and then because we're dividing further by S, we put at the top, and that reduces this to 2, giving you kilograms multiplied by meters per second squared, which is what we've got here, and that is F equals MA. If you now multiply that by seconds, we end up with F equals mv. So this is your momentum. This is your Newton's force law. Length is quite self-explanatory. Then what I did was from these two diagrams, we've got the electronic, the standard resistor, capacitor, and inductor, but empty free space. Remember, this is all about empty free space. There's nothing to do with real electronics. If you want to use real electronics, you're going to have to find the relative permeability and put it in there, and the permeability is going to need to go into that one. Other than that, you can use this for doing transmission lines like coaxial cables, etc. But I am treating this as empty free space. So what I did was I said, well, look, I want the charge, and I want the mass in kilograms, and I need a charge to mass ratio. So I've taken the M for electronics, and I've taken the M subscript little m for mechanical memristance, which is why it's the Christmas tree shape rather than that one. And I said I want the charge to mass ratio. So from differential calculus, I took the tiddly bits from here at this end, and I took the tiddly bits from that end, and I called that the ratio. And that is what we've got here, and which is why I put a little 0 in, because this is the charge to mass ratio of empty free space, which is what you found inside J.J. Thomson's evacuated tube when he put it through the Helmholtz coil. Which, by the way, the reason why I called this 13.65 in one of the videos and not 136 is because when you go back to J.J. Thomson's original experiment and you follow his mathematics, you can understand why this number came out, which is the fine structure constant, and you understand where this comes from. Because in the CGS units, you divide this by 10, and then you end up with this value 13.65, which is the diameter of the coils in the Helmholtz coil. And you'll understand that the 137 is slightly higher because that is actually from a quadratic calculation when you go from linear to polar coordinate calculations. It's quite a find that for me. I thought that was amazing. So we've talked about the electronic SI units. Please feel free to use these diagrams and do what you like with them. Just please keep my website name in there, because everything is tied into Buzzword Salad with a single Z. That is all of that. Remember that Rm is the coefficient of drag, and that the epsilon m is usually called K, isn't it, when you're talking about Hooke's law. And this is the Hooke's law for electronics. It's the same thing. It's all the same thing. It's how springy is the spring, and how much tension is there in the voltage tension. How much electricity tension is there in the displacement current inside there. So now you can see how the SI units can now be plugged into Maxwell's equations, and you should be able to take all this gold stuff and plug it all into here and do exactly the same thing and get the same answers. I think that covers everything. Oh yeah, we've got one small thing which we can do is we can actually use this in anger. A little sheet here. This is a nice little one. So what we're going to do is we're going to calculate Planck's constant. If you ever wondered where Planck's constant comes from and why it is a value that's inside the black body radiation curves, is because it comes from the spin angular momentum of this one. That is, it's all to do with this. Okay, and we're going to prove that now. So what we do is we say that the force of the electron is equal to the Coulomb constant, which is for electricity, just as G is for the gravitational one. We have Q1, Q2 divided by the square of the distance between them, and because Q1 equals Q2, we end up with this, which is QE squared over R squared. And remember, KE is 1 over 4 pi epsilon naught, and the epsilon naught and 4 pi is actually a residual left over from when you convert CGS to SI, because there's this factor of 10 that falls out, because you've got 100 centimeters per meter, and you've got 1,000 grams per kilogram, and so you end up with this 10 to the power of 7. So that's that. We know what this is. This is E over B is E over B, which is QV. Here we've done B over E. So you've got, which is the velocity of the electron. That's that little person up there. That's the velocity of the electron going through J.J. Thomson's experiment. If you take the square root of that, what you end up with is R, and you can plug that into here, and this will actually give you this equation, that the reduced Planck's constant is not very clear, but that is actually a slash through there because it's Planck's constant over 2 pi is actually the Coulomb force multiplied by QE squared over QV. And if you plug in the definitions of what QE are, and you square all this, and you take QV and you square all that, what you'll do is you will find that that it all resolves down to a very straightforward little equation involving the speed of light, lambda E and lambda B. And that is, I think, is quite amazing. Obviously multiply that by 2 pi, multiply Fe up here by 2 pi, and you will end up with Planck's constant H. Now the interesting thing about Ke is, what was I going to say about Ke? There was, yes, is that Ke and capital G are very similar in their linking, because you would get mass 1 times mass 2 over the distance between them for the force of gravity. And so this mechanical stuff and this electronic stuff, the equations are very similar for a very good reason. Thank you very much for listening. Were you paying attention, 007?